Naive Bayes is neither naive nor Bayesian. Changed my mind. Welcome to this video on classification. My name is Kevin Fiesel, and I'm the proprietor of Catalaxy Services LLC, a consulting firm which specializes in work all across the data platform space, especially SQL Server. There's a joke about the dead and unlimited USSR, the Union of Soviet Socialist Republics, that it was 4 lies and 1 name. Well, when it comes to the naive Bayes algorithm, there are 2.5 lies and 1 name. Let's break it down and you'll see through the lies, while learning that this is regardless a rather practical algorithm in spite of its name. First lie, naive Bayes, not a single algorithm. It is a series of algorithms. Granted, I will probably slip at least once during this video and talk about the naive Bayes algorithm, but there are some minor differences in this class of algorithms, with certain variants being better for multi-class classification, others for binary classification. If I do slip, you're welcome to correct me in the comments, and I'll feel exactly the appropriate amount of shame for that mistake. All of the naive Bayes algorithms follow the same general form. First, they are all probabilistic. We calculate the probability of landing in each output category, that is, of selecting each label, and we choose the highest probability from the set. Second, these probabilities derive from Bayes' theorem. This is where we get the Bayes in naive Bayes, and where we get our second lie, but let me hold on to that until the end so that we don't get lost in the weeds here. Third, we assume that all features are independent and there are no correlations between features. This is where we get the naive in naive Bayes. I rate this as half of a lie. Technically, it is correct, but I think it undersells the importance of doing the necessary feature engineering legwork before training a model. So before we get into the demo, I do want to walk through a detailed example of how this all works. Let's suppose we have a data set with some historical weather information. We have the outlook, whether it was a sunny day, a rainy day, or an overcast day. We have the temperature, which can be hot, mild, or cool. We have the humidity level, which can be high or normal. We have a question of whether we would call it a windy day. And finally, we have a last question. Did we play golf that day? What we're going to do is try to use this input information to help us understand which weather conditions are more or less conducive to playing golf. Then, given some set of weather conditions, we'll predict whether or not we'll go out and hit the links. I have 14 examples of data here. That's a lot to cram in on a whiteboard, so hopefully you can see it. I also realize it's not a lot in the grand scheme of things if we were doing this as a real problem. But given that our goal is to determine, based on input conditions, whether we should play golf, we should probably come up with a process to figure this out. With naive Bayes, we can do just that using the following steps. Our first step is to find the probability in general that we will play golf. In Bayesian terms, this is the prior probability, the starting point or the current point of our proclivity to golf. Next, we want to find how likely we are to golf in each condition for a given variable, independent of the other variables. In other words, for each value of outlook, how likely are we to golf? For each value of temperature, how likely are we to golf? And so on, covering humidity and wind as well. Finally, once we have all of these values, we plug that data into the formula for Bayes' theorem and we get our answers. I'll do all the math for you so you don't have to try rewinding the video over and over and looking back at that chart. The first thing we want to calculate is the prior probability. There were 14 events in total, and we golfed 9 out of those 14 times. Now I'm showing this in a couple of ways. First, I'm showing you a count of events. Second, I'm showing you this as a probability ratio, because that later form will come in handy as we move on. Now let's move on to the next step, where we take each feature independent of the others. I'll start with outlook. There are 3 total values for outlook: sunny, overcast, and rainy. For each of these, I want to break out the value by my 2 label values, indicating whether I played golf or not. I played golf on a sunny day twice, but chose not to play on a sunny day 3 times. I played on 4 overcast days and did not skip golf day at all when the outlook was overcast. For rainy days, I played 3 times and skipped twice. Now I can calculate the probability ratio of it being sunny given that I went golfing, or it being sunny given that I did not go golfing. Remember that I went golfing 9 times in total and I skipped 5 times in total. Thus, the probability of it being a sunny day given that I went golfing is 2 out of 9. And the probability of it being a sunny day given that I did not go golfing is 3 out of 5. We repeat this process for each of the outlooks, and you can see that the probabilities of yes and no add up to 1, as they must. Let's repeat this process for temperature. We break things out by the 3 temperatures and keep track of those results independent of outlook or any other variable. This gives us a new probability distribution given that we went golfing, and one given that we did not go golfing. The humidity table only has 2 entries, high and normal. For normal humidity, we went golfing 6 out of 7 times. For high humidity, we went golfing 3 out of 7 times. And you can imagine that the final variable, whether it was windy, has a similar effect. It was windy 6 out of the 14 total days, and we skipped golf 3 of those 6 days. For non-windy days, we went golfing 6 out of 8 times. Now that we have all of these factors, well, what do we do with them? At this point, we need a prediction. Let's look outside the window and say that today's outlook is sunny, the temperature is hot, the humidity level is normal, and it's not a particularly windy day. Given these conditions, are we likely to golf or not? All of this starts with Bayes' theorem. We have the probability of B given A, which is something we call the posterior probability, or the probability we determine after new information comes in. This tells us the probability that we see hypothesis B given some new data A that we have collected. The formula for calculating this involves 3 factors. First, we have the probability of data A appearing, assuming that hypothesis B is true. We multiply that by the probability that the hypothesis is true regardless of the data. That's P of B. This bit is also known as the prior probability, and we calculated that earlier. Finally, we divide by the probability of seeing data A at all, regardless of whether the hypothesis is true. We can apply this formula to calculate the probability that we go golfing given today's conditions, and the probability that we do not go golfing given today's conditions. The formula for going golfing is as follows. We take the probability of the outlook being sunny, given that we are going golfing, multiply by the probability that the temperature will be hot, given that we are going golfing, multiplied by the probability that humidity will be normal, given that we are going golfing, multiplied by the probability that it will not be particularly windy, given that we are going golfing. And finally, we multiply by the probability that we go golfing in general. And then we divide by the probability that we will see these particular weather conditions in our area. Next, we calculate the probability we do not go golfing given today's weather. This formula looks very similar, except that now the probabilities are conditional upon us not going golfing, and we're multiplying all of this by the probability that we do not go golfing. But the denominator is the same. And that's a good thing, because here's the dirty secret. I don't know what the probability of getting today's conditions looks like. If I know what P of T is, I could actually deliver on proper probabilities, but it turns out I don't. Fortunately, it also turns out that I don't have to care. Remember that we're just asking, is P of Y given T greater than P of N given T? Or is P of N given T greater than P of Y given T? Because we're performing an inequality check, we can simply drop the common denominator and check which of the 2 numerators is bigger. Let's put this all into numbers. For our top formula, we know that the probability of the outlook being sunny, given that we are going golfing, is 2 out of 9, so I can fill that in. The probability of temperature being hot, given that we are going golfing, is 2 out of 9. The probability of normal humidity, given that we are going golfing, 6 out of 9. And the probability of not having heavy winds, given that we are going golfing, is also 6 out of 9. Finally, our prior probability of going golfing is 9 out of 14. Multiply all of that together and you end up with 0.0141. I'll quickly fill in the values for the no case. 3 out of 5 for a sunny outlook, 2 out of 5 for hot temperature, 1 out of 5 for normal humidity, 2 out of 5 for limited wind, and 5 out of 14 on general principle. Multiply all of that together and you end up with 0.0068. No matter what the common denominator is, the probability that we will go golfing given today's conditions must necessarily be higher than the probability that we will not go golfing given today's conditions. So it's time to hit the links, or at least hit the demo notebook. But first, I did promise to talk about lie number 2, how, despite the name, the algorithm isn't really Bayesian. Now is as good a time as any to talk about it. When I showed you Bayes' theorem, I mentioned prior and posterior probabilities. The whole idea of Bayes' theorem is, as we receive new information, we update our prior probabilities based on this new data and use it to adjust our expectations around the correctness of a given hypothesis. The problem with the naive Bayes series of algorithms is there is no new data. Our prior and posterior analysis both use the same training data, so we never really adjust our available information. Even more, the prior that we develop is just a maximum likelihood estimate of the training data. We're not learning anything about a probability distribution, but we're instead falling into the frequentist trap of assuming that we can simply run a bunch of tests and unravel the mysteries of the universe. Why, yes, my soapbox does have a picture of Thomas Bayes on it. Why do you ask? Anyhow, let's go to the demo. In this notebook, we are going to look at the categorical naive Bayes algorithm, one of the class of naive Bayes algorithms. This is in sklearn.naive Bayes. Our next cell performs the same data prep that we've done a few times already, breaking out x and y variables. But after that, things change quite a bit. In order to use categorical naive Bayes, we need to make sure our input data is, well, categorical in nature. We know that there is a mixture of categorical and continuous features in our dataset, as we can see here by getting the number of unique values per feature. Some of these features have 100 or even 200 unique values, and if I moved forward with the data as is, I'd end up with 205 unique classes. I can use the describe function to get some basic information on each continuous variable, including a 5-number summary. With this information in mind, I want to give you 2 options for how to proceed. The first option is to perform 2 separate naive Bayes calculations. The first would take all of the continuous variables as inputs, and then you would generate pseudo probabilities from them by building a Gaussian naive Bayes model. Then, you would create a second categorical naive Bayes model using the categorical features and generate pseudo probabilities based on that model. Your final output would be multiplying the output from the continuous model by the output from the categorical model. This works because we assume features are independent, and this gives us a way to incorporate both types of data. The other option would be to bucketize our continuous variables, turning them into discrete categories. Then we would have just one categorical naive Bayes implementation to worry about. If you ask me for advice on this, I would ask if your goal is to maximize accuracy or get a reasonable result reasonably quickly. If it's the former, then build the 2 separate models and take advantage of the additional information that you have in those continuous variables. If you just want a good enough result quickly and easily, follow me into the second approach. The mechanism we are going to use is the funhouse mirror version of what we did for k-nearest neighbors and logistic regression. For those algorithms, we converted categorical string data into numeric categories. This time around, we're taking continuous floats and converting them into numeric categories. To do that, we'll use the k-bins discretizer. I'm setting the number of bins to 5 and encoding them ordinally, so we will have 1 column of output per column of input, and the values in that column will range from 0 through 4. Setting the strategy to uniform means that each bin will have an identical width, though we might not have the same number of data points in each bin. The last part about subsample equals none is that I will use all of the training samples to compute quantiles. It's a small data set, so subsampling is neither necessary nor helpful. Now that I have my encoder set up, I can select all of my floating point types and fit the data to my encoder. Then I'll transform the data and put that into a codes variable. I'll also define feature names for the columns, using the same set of input column names that I just transformed. Finally, I will concatenate the categorical string data types with my new categorical numeric data types, and I end up with 215 rows and 12 columns, just as I had before. But one difference is, if I look at the SSC_P column, I can see that there are 5 unique values, rather than 103. Furthermore, if I look at the number of unique values per column in X, we can see that everything ranges from 2 to 5. Categorical naive Bayes will play with this data a lot nicer now, so let's get back to it. The next step is to create the classifier. In order to instantiate an object of type categorical in B, we need to pass in 2 variables, alpha and min categories. Alpha is an additive smoothing parameter, something called Laplace smoothing. We didn't talk about it in the classroom, but briefly, it's what we use in cases where we have 0 instances of a thing occurring. If we follow the basic naive Bayes formula as is, we can end up in a weird situation where, due to there being 0 cases of some feature showing up for placed students, we cross-multiply and end up with a probability of 0 for placement. But if some second feature never shows up for non-placed students, we cross-multiply that and end up with a probability of 0 for non-placement. We would have 0 probability of either outcome, but we know one of the 2 must happen, and that causes a hard error. Laplace smoothing adds a small value to every part of the equation, guaranteeing that we never have a 0 value without affecting the comparison. I have the alpha set to 1, so Laplace smoothing will happen. Also, min categories is an array of the number of categorical values we expect from each feature. We'll need that in case something shows up in the test dataset that we never saw in the training data. Given how few records we have, that's a likely outcome. The next thing we need to do is convert the categorical string data into ordinal data. Remember that for the other algorithms, we used one-hot encoding to transform categorical data into a series of 1s and 0s, representing whether that category appeared. Categorical naive Bayes expects categories, and so we don't need to do that. Instead, we can simply fit all of our columns and get a set of numbers out, representing category values. One quick thing to note is, some of my data is already in the right shape, but it doesn't hurt to run it through a second time. After fitting and transforming the data, we end up with 215 rows and 12 columns, just as before. And the data itself is now an array of input features. Like the prior cases, I will perform label encoding on my output data. Then I'll split the data into training and test subsets. We can take a quick peek at the training data for X to ensure that things look reasonable. And they do. So let's train a model. The training process is a simple fit method call on the classifier. Now that I'm done, let's see how we did. Using the accuracy score function, we can see a high level accuracy of about 83.1%, which is pretty good. Drilling into the confusion matrix and classification report, we have some more detailed results. I'd like to scroll down to this table that I've put together, looking at each of the 4 algorithms we've used for this part of the series. Naive Bayes does a better job at finding candidates who will not place than k-nearest neighbors, but it is a little worse than logistic regression and XGBoost. Meanwhile, it's right in the thick of things when it comes to catching people who do place in jobs after graduation. It's a little more likely than these other algorithms to say incorrectly that a candidate will receive a placement, failing on 6 cases versus 4 for logistic regression and 3 for XGBoost. But these results nestle in with the rest of the algorithms we've seen so far. That was naive Bayes. Yes, it is 2.5 lies in one name, but it's still a good set of algorithms nonetheless, for a few reasons. It is quick. It is easy to implement, and the results are at least adequate in most cases and very competitive in some cases, like what we saw in the demo. Incidentally, if you want to dig deeper into naive Bayes, I have an entire presentation on the topic that you can check out. The next video covers one of my favorite classification algorithms, and not just because of the name. We'll have links and show notes in the description below, and until we see each other in the next video, take care.